In this video, we're going through my project where we build a neural network using only NumPy. We'll be discussing how combining simple linear equations can result in a neural network that's capable of predicting almost anything. So let's start by making the most basic unit of a neural network, a single neuron or hidden unit.
A neuron, or a hidden layer unit, is basically a linear equation. Y equals W times X plus B, where X is the input, W is the weight, and B is the bias. The values W and B are called parameters. They're what the model learns during training. At the start, we usually initialize them with random values. During training, these values are adjusted so that the neuron gives better and better predictions.
First, we'll be building a neural network with just a single neuron, and we'll train it to guess the values of a sine function. So, let's start by writing a simple function that returns the sine value of any given input x.
Next, we'll create a function to generate 100 random values between 0 and 5. This will be our input data. And finally, we'll make a function to plot both the actual sine values and the predicted values, if provided, so we can visually compare how well our model is performing.
All right, so here we've defined a simple class called hidden unit 1 by 1. This represents a single neuron, one input, one output. In the constructor, init, we initialize the neuron with a bias and a weight. These are the parameters of our linear equation, y equals W times X plus B. There's also an update method, which lets us manually change the bias and weight, helpful during training when we need to adjust the parameters. Finally, the output method takes an input x and returns the result of the linear equation, essentially what the neuron predicts given that input.
Before we train our neuron, let's talk about one very important concept in machine learning, the loss function. A loss function tells us how bad our model's predictions are. It's like a score. The higher the loss, the worse the predictions. We want the model to make predictions that are as close as possible to the actual values. So during training, we try to minimize the loss. In our case, we're using the least mean square loss, or LMS for short. It works like this. For each predicted value, we calculate the difference between the prediction and the actual value. We square that difference so negative errors don't cancel out. Then we take the average of all those squared errors. This gives us one number, the loss, that tells us how far off we are overall. For example, if our predictions are perfect, the loss will be 0. But if our model is way off, the loss will be a large number. So our goal during training is to adjust the model's parameters, the weight and bias, to make this loss as small as possible.
Now that we have a loss function, the next question is, how do we minimize it? That's where gradient descent comes in. Gradient descent is an algorithm that helps our model learn by making small adjustments to its parameters, like the weight and bias, to reduce the loss. Imagine the loss is like the height of a hill. Our model is standing somewhere on the slope, and we want it to get to the bottom, the lowest possible loss. At each step, we calculate the slope of the hill, called the gradient, and then we move slightly in the opposite direction. That's why it's called descent. We're going downhill toward a better model. Now, let's take that idea and apply it in code using this class, hidden layer 1 times 1 times 1. This class is like a mini neural network with just one neuron, or hidden unit. We pass in initial values for weight and bias, a loss function, and an optimizer, which in our case is gradient descent. The forward pass method simply runs the input through our neuron and returns the output. In the train method, we loop over the number of epochs, or training rounds. For each epoch, we run a forward pass to get predictions, calculate the loss, and save it to track how the model improves. Next, we compute the gradient. That's the slope of the loss with respect to the weight and bias. This tells us how to tweak them to reduce the error. Finally, we update the weight and bias using gradient descent, subtracting the gradient times the learning rate. And after training, we return the history of loss values so we can see how much the model improved.
First, we generate our training data, 100 random values and their corresponding Sine values. This is what our model will learn from. Next, we create an instance of our one neuron model. We initialize the weight and bias with small random values. Multiplying by 0.1 just helps keep things stable in the beginning. We also pass in the least mean square loss function we defined earlier. Now, we train the model. It runs for 1,000 epochs using a learning rate of 0.01. The train method returns the loss at each step, so we can see how the model improves over time. Once training is done, we do one last forward pass to get the final predictions from the trained model. Here, we plot both, the true Sine values, in blue, and the model's predictions, in red or another color. This shows how closely the model has learned to match the Sine function. And finally, we plot the training loss over time. If the loss keeps going down, it means the model is learning. A flat or increasing loss might mean something's wrong, maybe a bad learning rate or too few epochs.
In the previous version of our model, we had just one neuron. Now, we're taking a small step forward by adding 2 neurons in the hidden layer and 1 neuron in the output layer. This makes our architecture a 1 by 2 by 1 network. But before we jump into the code, let's quickly understand 2 important concepts: output weights and bias, and activation functions. First, the output weights and bias. After the input passes through the hidden layer, we get 2 values, one from each hidden neuron. These values are then combined using a weighted sum. That means we multiply each hidden output by its own weight and add a bias term. Y equals W1 times H1 plus W2 times H2 plus B. This final value is the model's prediction. Now let's talk about activation functions. Inside each hidden neuron, after calculating the linear combination Z equals WX plus B, we pass it through an activation function, in our case, the hyperbolic tangent, or tanh. The tanh function squashes the output to a range between -1 and 1. This helps introduce non-linearity into the model, which is essential for learning complex patterns like the sine wave. Without activation functions, no matter how many layers we stack, the model would just behave like a fancy linear equation, and that's not enough for real-world data. So now that we understand how the hidden layer transforms inputs using tanh, and how the output layer combines those with its own weights and bias, let's put it all together and build our hidden layer 1 by 2 by 1 model.
After training, the 1 by 2 by 1 model produces a nonlinear output that closely follows the sine wave. This happens because we use 2 hidden neurons with the tanh activation function, which introduces nonlinearity. Even though the final layer is linear, the nonlinear transformations in the hidden layer allowed the model to learn complex patterns beyond straight lines.
Now that we've seen how a 1 by 2 by 1 network works, the next step is to make our design more flexible. Instead of hard-coding just 2 hidden units, we'll build a generalized class that supports any number of hidden neurons. This means we can experiment with different architectures like 1 by 3 by 1, 1 by 5 by 1, or even 1 by 10 by 1, all using the same reusable code structure. Each hidden unit still works the same way, but now we manage them in a loop. This makes our model more scalable and adaptable for different tasks or levels of complexity.
As we increase the number of hidden units in the layer, from 3 to 5 to 10, the model becomes more flexible. With just a few neurons, the network captures the general shape of the sine wave, but may still look a bit rough. As we add more units, the network gets better at fitting the curves smoothly and accurately. More hidden units mean more internal combinations of features, which allows the model to approximate the target function with greater precision. However, too many units can also lead to overfitting, so there's always a trade-off between model complexity and generalization.
To end this video, we train a larger neural network, a 1 by 100 by 1 architecture, on the sine function over the range from 0 to 10. With 100 hidden neurons, the model now has enough capacity to learn even more complex variations in the curve. But there's one more important detail: initialization. It turns out that how we initialize the weights has a big impact on training performance. So instead of using completely random values, we apply Xavier uniform initialization, a technique designed to keep signals balanced as they flow through the network. With this setup, the model learns faster and produces smoother, more accurate approximations of the sine wave. This demonstrates how both network size and good initialization play key roles in building effective neural networks, even when working with just NumPy.
Thank you for watching this video. If you'd like to explore the code yourself, check out the link in the description for the full source code.